that, and thanks for the invitation to come out and talk. It's really great to be out here. This is my first time visiting, although I know many of you already through some of the work that we've done together. Yeah, so Alex, so sometimes I tell I taught a statistics class for a long time at Cornell, and I would tell the students at the beginning of the year not to try to cheat on their exams because they pay me a lot for pattern recognition, right? And nevertheless, some still tried. But anyway, today I'm going to be talking a little bit about the effects of ocean temperature on spatial density of summer flounder, Paralichthys dentatus, in the mid-Atlantic. And summer flounder you might know as fluke. That's the common name that people, very popular fishery. So there's both commercial and recreational fishery on this fish. It's about a 50-50 split. And of course, that creates some controversy, right, about who gets the fish and whatnot. As part of my motivation, I'm a statistician, but I work mainly on fish population dynamics, mainly in marine systems, but I have projects going on in the Hudson River estuary, the Great Lakes, trout, as well as I have a student working on salamanders and rattlesnakes, which is kind of fun, and other students doing some work on elephants. But all of them are doing the spatial distributions of various kinds of things. And I teach the introductory course in statistics for the students at Cornell, but also teach fish population dynamics course and a spatial statistics graduate course. So we'll talk a little bit about that as we go through. So part of my motivation here is I was actually working with the Save the Summer Flounder Fishery Fund, the group of recreational fishermen that fish for summer flounder. They were really needing some help understanding the population dynamics associated with summer flounder, and so I was there at a number of different meetings sort of helping them get the communication going on. And then in the end I ended up building a sex-age length-specific model for summer flounder in the mid-Atlantic. And so that's been a very exciting thing. And I've given talks on that elsewhere as well, but today I'll focus on this one. This is some work my graduate student, that's pronounced Summer, Dean, was working on. So the name of her chapter was, Is It Too Hot for Summer? So she kind of played off of that and did some work. And then my postdoc, Verena Jaus, and I kind of built on that and expanded the model a little bit and are putting it together for submission into ICES, and it's just about ready to go there. Now, so Verena is still at Cornell with me as a postdoc. And Summer is working for IBM now. Yep, she went to the dark side. So you know IBM doesn't do computers anymore, they do data. So this is the challenge, and many of you know this, is that you get trained in statistics and so forth, and then it's more lucrative to go into other areas than fisheries. But fisheries is so much fun, right? So why not? So part of my motivation here was really to do a couple of things. One was I was wanting to see what the spatial distribution of summer flounder was and how climate change was affecting that. And I knew something was going on, and there was a number of different people who were exploring this to see what the effects are. So I wanted to take a look at it. But one of my other motivations was that I do spatial statistics, and one of the things that I had created when I was in graduate school was a spatial geostatistical assessment of Alaska pollock in the Bering Sea. And so I wanted to take a look at that, but it was computationally very intensive to do at the time. Nevertheless, I did it, and it was just one snapshot in time. So since that time, I've continued to work very heavily in the acoustics area. My colleague and I, Lars Retstam, have created the standard operating procedure for doing acoustic assessments in the Great Lakes, for example. I'm not an acoustician, I'm a statistician, but I work on acoustic data. So I worked with Mike Jeck on herring in the Atlantic and other places. And so here I've constantly been in the situation where I've been wanting to look at how things change in space over time, all right? But you can imagine if you're doing some kind of spatial thing, typically you're doing a geostatistical one. If you have 1,000 observations, that's 1,000 by 1,000 matrix that you have to invert, and all of this kind of stuff. It takes a really long time. I'm also interested in Bayesian approaches too, which often involve Markov chain Monte Carlo, which is sort of a random walk around the probability field to find what we're going on. Of course, this random walk takes a long time, and these MCMC approaches take a long time as well. So I was in Norway for a sabbatical, and while I was there, I learned about this method, INLA. It stands for Integrated Nested Laplace Approximations. And it turns out that you can use this to approximately do the integration of the normal curve in a very straightforward way that doesn't involve the MCMC algorithm. So as a result, you can do an analysis over space and time. And so in this particular context, I did it with a conditional autoregressive model, which is basically applied to a lattice. So a lattice is like states in the United States or counties in the state of New York or something like that. So this is an application of INLA in the lattice context. But you can also do geostatistics, so Kriging. And so currently I'm developing something like that for Kriging the spatial temporal abundance of cod and capelin in the Barents Sea, and then maybe cod in New England. We'll see how that turns out. So I'm going to send this book around. So what I'm talking about today is conditional regressive models, and I'll talk about the book that's summarizing that there. And this one is the geostatistical one. All right, so I want to send this around just so you can kind of take a look at it. And you can see there's code in there, and there's other things. And from my way of thinking, this stuff is rather new. And I'm used to doing the geostatistical stuff in something like R or ArcGIS or something like that. And so I'm having to do now some of the crosswalk between my old standard ways of doing it and this new integrated nested Laplace approximation way of doing it. And so it's a little bit tough, even for me, who's supposedly an expert in this area, making this kind of crosswalk. But hopefully today, I'm hoping you see the advantages to using something like this for looking at something like summer flounder, but also the advantages that might be open to you, because I know a lot of spatial work goes on here, that you might find this advantage to you, and here are some resources to get at that. So we're identifying ecologically significant physical oceanographic variables that best explain observed spatial temporal density of summer flounder. So this is a lot like doing a regression, except at the same time I'm trying to take into account the spatial correlation. The belief that if I know what the number of fish in one area, that should give me some information about the fish next door. And this works perfectly in fisheries because, like, if you're a fisherman and you're fishing, you don't want to go very far away from there if you're successful, right? If you're not, then you want to move, right? So this idea of spatial correlation is just really inherent in what we do. The other, of course, as I just mentioned, is the development of the method for space-time modeling using the INLA, the integrated nested Laplace approximation for the car, the conditional autoregressive modeling, all right? So as I'm going through, stop me anywhere along the lines if I skip over something that seems kind of cryptic, and I can kind of go back and we can talk a little bit about it. So summer flounder is distributed through the mid-Atlantic bight, so Virginia, Carolina, and so forth, a little further north from you guys. And, but it's been found in the Gulf of Maine all the way down to here, I think. So in the 1980s, the stock was to be determined to be overfished. This is actually the harvest, all right? So one of the things that happened is they cut the harvest in half. We were talking about controlling harvest. And it really had a significant impact, and I think did great things for the stock. So the quotas were reduced, size limits were put in, and subsequently there was an increase in spawning stock biomass. And you know, why didn't they do this sooner? Well, frankly, the law was not strict enough, and so they added a few more sticks to the law to kind of get it going, and I think this affected the fisheries throughout the United States, and and summer flounder was one of them that did that. Now, I have another presentation that's actually a PowerPoint that goes through, and actually we have animation for this, but unfortunately on the PowerPoint that I have, this is one that, this talk is one that that Verena actually gave. We went to a meeting in the Ecological Modeling Conference in Salzburg, Austria, and so this presentation, this is why it's supposed to be a 15-minute presentation, but if you're long-winded like me, it takes a little bit longer to do that. But nevertheless, some of the information that went into this were sea surface temperatures, depth, bottom temperature, bottom salinity, and we had 2 data sources, spring and fall surveys from National Marine Fisheries Service. So in many ways, this is basically like a regression where I'm putting these various things in and taking that into account, but I'm also taking into account the spatial correlation, which makes the problem a little more tougher, certainly computationally a little more intensive. But what we end up doing is, in this case, the sea surface temperature stuff was condensed into information that could be used to look at, this is relative abundance from the surveys. Actually, this is temperature too. So this is temperature from the satellite data. This is temperature from the trawl data that National Marine Fisheries Service does, and so we're following that as we go through time and try to make sense of these things. But we ask ourselves: is the information here helpful to the information here in some kind of way, or are they all operating independently of one another? And of course, if we believe it's all independent, then that actually increases the power, but in fact, we know fish and temperature are correlated to one another, and so we must have to take into account changes in sort of sample size effectiveness going through there. All right, so here's the model. And you're all going, yes, finally. All right, so it looks kind of complicated, but let me walk through it and you'll see what the different elements are, right? So this is our response variable, which in this case is like the catch per tow. We're trying to predict the catch per tow in the National Marine Fisheries Service surveys, right? So number of fish caught per standard length of haul. And this part right here should look familiar. It's just the linear input part. So here we'll have sea surface temperature, bottom temperature, salinity, depth, other kinds of things coming into play. And then we have all of this other stuff that takes into account many of the other things that are going on. And you might notice the ST subscripts here, so space and time is the way we're using it here. And typically, if you're used to something that's kind of like a mixed effects model, where you have a fixed effect and a random effect, all right? So that's kind of what we're doing here, only in a spatial context. So this is like the fixed effect. So the standard, so this would be the spatial mean for each of these areas over all time. And this would be the correlative part in space, all right? So this part here would be the standard one-time period conditional autoregressive spatially correlated model type of thing. This over here is then the time component, so fixed and random. And so this part here is what's remaining the same through time, whereas this is more like a random walk component, all right? Finally, we have this interaction term here. So I'm representing it with one symbol, but it's actually all of the different things all combining together. And this is where all of the heavy overhead comes in terms of the computational parts. So part of what I was looking at was like, oh, here I have a really great data set here. Let me see how far I can take this in terms of the model complexity and what information is there. And do we see anything different in doing it this way with the various spatial and temporal autocorrelations versus leaving that out? So we did all of that. So that's nice. And it's basically a kind of fancy linear model, if you will. And then the other component is that in this particular case, there was a lot of zeros. Not surprisingly, we have that happen a lot in fisheries. So what this is a zero inflated Poisson. I have to mention here that, you know, I do teach statistics class. I do have this one example of a Poisson distribution that's biological in my class. It's elephant mating, all right? And so that really follows nicely a Poisson distribution where the mean is equal to the variance, all right? That's one of the things that we look at Poisson and identify it that way. I've never seen that really in reality. I've always seen the variance greater than even though it's count data. And so everybody comes in, oh, it's count data, it must be Poisson. No, you know, it's usually, so quite often we have a couple of different ways of inflating the variance. This particular one basically has two elements of the model. One element is the probability of finding a zero, and then the other is the probability of not finding a zero, and then if it's not zero, what the number is. But another way of doing this is like a negative binomial or other kinds of things. So what I'm saying is we're going to do a kind of linear model, but this is like a generalized additive or a generalized linear model where the underlying distribution of the response variable is not Gaussian, it's Poisson, zero inflated Poisson. So just a little bit of an aside there. So you can see there's some sophistication here working in the background, but basically it's a regression that we're looking at when we're looking at this. So one of the things that we have to do when we're doing the conditional autoregressive type of model is specify a neighborhood. And so there's a number of different ways to do that. Basically what we're doing here is looking at the centroid and taking it out to the next centroid, all of the next centroids beyond it. And we have a 30-mile radius here where if it's shorter than 30 miles, it's included as a neighborhood. There's other ways to make neighborhoods, like if my boundary is next to your boundary, we're neighbors. But here we're actually using distances. And so you can kind of see in the background here, this is in the gray, maybe you can't see it in the back. I can see it up here. You can come up and see it if you like, is the National Marine Fisheries Service statistical areas. All right, that's my lattice. And then I'm specifying a priori what the neighborhoods are, and then I'm going to use a correlation matrix that relates one area to the other based on the strength of the correlation and the distance, all right? So this is a kind of simplification of what you do in geostatistics. In geostatistics, you typically have some kind of correlation that drops off with distance. That's what you do kriging. In the geostatistics, you're typically looking at a continuous sort of area. Here it's very discrete, and so we're looking at attributes that are associated with between one and the other. So as something I'm constantly trying to acknowledge in myself, but also for others whose publications I'm reviewing, that we're imposing some information on this by defining what the neighborhood is, for example. And so every time we do a model, every model has assumptions. Even if we're assuming it's Gaussian, that's an assumption, all right, that adds structure. And again, back to the Poisson example, if we're doing a regression, somebody came into my office the other day, they were doing a Poisson regression, it wasn't working, and that was because they were assuming that the variance was equal to the mean, and it wasn't, and so they were getting really strange answers as a result of that. So anyway, I'm telling you, I'm trying to be upfront that I'm imposing some structure on this, and one of the challenges that I've had is a lot of the books that have been coming out on this stuff assume the correlation is 1, and it's just based on distance. I felt really uncomfortable with that because all of my previous work has been trying to estimate what the correlation actually is. So one of the exercises I did through this particular work was to compare the assumption of a correlation of 1 versus the allowing it to be estimated, and so you'll get a chance to see that contrast between those two. So we get a chance to see what the neighborhood looks like. All right, so I went to Norway. I was working with Sam Subby there at the Institute of Marine Research. That was a lot of fun. And then these guys in the northern part of Norway were doing this INLA stuff, and they were offering a workshop, and I thought, well, I'm in Norway. Why don't I go? So I did. And it was fantastic, a lot of fun. So what is it? It's called Integrated Nested Laplace Approximation. And really what it boils down to, this is kind of a Bayesian formulation associated with this, really where we're trying to predict the observations that we have based on a set of input data, but also a set of parameters. The key assumption associated with INLA stuff that allows you to work in. And so you can't do everything with INMLA. There's a lot of stuff you still only have to do, can do in the MCMC format. But here, if you can structure the model such that the parameters themselves follow a Gaussian distribution, and quite often they do because they're like summary statistics, they're like means. And so through the central limit theorem, if you have enough observations, these things are going to behave in a kind of Gaussian way. These are called latent Gaussian models, all right? If they're Gaussian, then we can approximate them. So the green here is a Gaussian curve. The dashed red line is the Laplace approximation. So Laplace came up with this. He basically created this polynomial. You may or may not know that it's impossible to integrate the Gaussian distribution. There's no closed form solution. So if you go to the CRC books or any place or even do it online, it's an approximation simulation of what the Gaussian distribution is doing. Laplace figured that if he did it with a polynomial, he could do the integration, which he could. So this allows us to actually get the probabilities without having to do, let's say, a Markov chain Monte Carlo or some other more sophisticated approaches. So you can imagine, if you're familiar with doing Markov chain Monte Carlo, quite often it's like a random walk. So picture a mountain. That's the binomial Gaussian distribution. Picture yourself just kind of wandering around at random over 100,000 steps. Eventually, you're going to get what the picture of the mountain looks like, but it'll take you a long time, all right? Whereas this goes right to it and says, this is what it is. So it saves you whatever it is, 100,000 steps in the computation, and that makes things a little bit faster. So this is what's being done here. Now, I want to do the connection to the conditional autoregressive model. And this is the standard thing you might find in Cressy or some other book. And really what it's doing is it's saying, hey, we're going to do this regression, response variable, catch per toe of summer flounder, predictors of sea surface temperature, bottom temperature, salinity, and so forth. We're going to try to estimate these coefficients. Generally speaking, I was going to say normally, but we don't want to do normality here. Generally speaking, right, this term here is epsilon, which is assumed to be independent and identically distributed according to Gaussian. This is still Gaussian, but it has an autocorrelation matrix that represents the correlation between each point and each other point. And now these points are identified through the neighborhood matrix. And so this matrix here is the connection between every point and every other point associated with this. And so this thing can be actually broken down into like an overall variance component associated with this. This is the weights matrix that depend on the distance between each neighbor. All right, this is the correlation, the thing I'm saying we should estimate rather than fix at 1. And then finally, this neighborhood matrix is the weighted neighborhood matrix. So this other one is really the diagonal weights associated with this particular element here. So you can see it's a variance covariance matrix that we're trying to get at. All right, so here's the results. All right, so we explored all of these kinds of things, and if you can just remember the first slide that had the different elements in here, what we're doing is all of the different combinations of things. So you notice maybe up here, I don't have this delta term, so I'm not doing any interactions up above. And then here I actually used year as an effect as opposed to a random walk, for example, and so on and so forth. I tried all of these things, including these really high-order interactions, which are really kind of complicated to try to understand. And in the end, these two are the ones that came out on top. So even though I had like a lot of data, these elements of the model with the interactions of the various spatial and temporal components were not really needed. So what does that mean? What does that mean? That means if we're kind of looking at this and we have things marching along with time, we're kind of expecting the different areas to sort of respond more or less in unison all the way through. It's not like, you know how, you remember this from stat class where If they're parallel, there's no interaction. If it's crossing, there is interactions. In this case, there were no interactions. So the time trends were all the same across all of the areas, but the areas themselves showed some differences. And these differences were actually related to the underlying predictors, sea surface temperature and bottom temperature. So we're kind of getting a little ahead of ourselves, but nevertheless, I tried 2 different kinds of models, the BZAG, York-Molly model, and this generic model. And really the difference between these two is the BYM model assumed a correlation of 1, and the generic allowed it to be estimated. In the end, the estimate was actually pretty close to 1. So it looked like I didn't really gain a whole lot by doing this, but I felt better doing it because I was actually estimating something that I thought should be estimated. If we look at the results themselves, of course, because of the similarity here, we're seeing that the estimates themselves in terms of sea surface temperature squared, and in this case, sea surface temperature depth and bottom temperature were all very similar to each other in both models, and significant from a statistical point of view. I was just sent this paper on what does a p-value mean, and there's this whole American Statistician volume on it, and one should never really, the argument there is one should never really use the term statistical significance any longer because people misinterpret it, significant as important. And we don't, so the way I always view it is it's measurable. That's the difference. So if we get statistical significance, that means it's measurable. And then we have to look at, in this case, coefficients to see what kind of change is likely to occur with a certain amount of change associated with a particular input. So I want you to notice a couple of different things before we go into this. One is the fall variables were different than the spring variables in terms of what was going in. And you'll see why in a moment. People often were challenging us and others too for using sea surface temperature when we're looking at a bottom flatfish. But sea surface temperature ended up in the spring being really important. And I put a squared term here. I could have put some kind of smooth, but I didn't do that. And to capture the effect of where a summer flounder might have low temperatures that they're not happy with, higher temperatures that are optimal, and then higher still temperatures that are not optimal any longer. So it covers that sort of a curve, which doesn't show up in the fall setting, but depth and bottom temperature do. And part of our justification, you can tell me whether it's right or wrong, is the mixing that's actually occurring. So there's more mixing in the spring, so the effect of sea surface temperature is more dominant there, whereas in the fall there's less mixing, and so depth, bottom temperature play a larger role. It's kind of interesting to see that coming through. Finally, looking at the DIC, it's kind of like AIC, the ACA information criteria. So what we're looking for here is numbers that are lower. Lower numbers are seen to be better. And so we're, of the two here, this is the lower. Of the two here, this is the lower. 2 different data sets, so I can't make comparisons between the two. And generally speaking, like AIC, one can kind of look at this and say, if there are about 2 DIC units difference, that's kind of like about a p-value of 0.05, if you do want to talk about p-values, all right? So, this is about a difference of 6. This is about a difference of 7 between the two, so it's probably, I don't want to say it, statistically significant difference between the twos, so I feel like some justification for actually including the estimate of the correlation in there to some degree. All right, so this is the output associated with both of those, all 4 of those, I guess. So up here is the spring predictions of summer flounder relative abundance, that's catch per tow. And you can see that the 2 models, whether I'm estimating the correlation or not, but still having correlation in both, is very similar. And similarly, the fall models are similar too. What strikes me, of course, when I look at this, and I'm thinking about it in terms of population dynamics, the current summer flounder assessment models include both of these trends as predicting what's happening with the stock. I'm not sure that's a good thing to do because it's representing different kinds of dynamics that are happening there. So that's one thing. The second is, here is the effective temperature on both. So the data is shown here for the spring and then the fall. And then this is the spring. And so you can see the sea surface temperature coming through very strongly. Here's the fall. And it's there too, but it's not coming through strong enough to capture the squared term. All right? There's just not enough there to capture it, so we're left with this. So I was satisfied with that too, in the sense that it's giving us some sense of how the fish are responding to the temperatures in these regions. And one of the things that we've noticed, for example, cod don't seem to be in New England anymore. Haddock seem to be doing fine. The summer flounder, instead of moving further north, they seem to be expanding. All right? There's fewer of them in the south, but they're still there. So there's some kind of expansion going on, and looking at this is really interesting. So we decided to apply this spatially so that we could make predictions over time. And we actually did this over the entire 20-year period that we have, but I'm only showing you 3 of each 20 years, all right? So you get a sense of what's going on. And so we can see here back in '93 the distribution, and gradually sort of we're actually seeing good news, sort of increase in abundance, right? That's coming through spatially as well as temporally on the previous plot. But we're actually seeing them move further north actually here, greater concentrations in the north. In the spring, we're seeing something similar, but you can see more dramatically the expansion that's happening here. So in the assessments originally, no information above this point was being used. And so I'm arguing now that we should be using the entire spatial distribution here when we're trying to assess the population dynamics of this stock. All right, so what were our conclusions? So it didn't take 15 minutes, so it took 35. So sea surface temperature is in fact a useful indicator of summer flounder density for both the fall and the spring survey indices. When I was working at the Halibut Commission, I always had this view of halibut being, bottom dweller too. But then we got these cameras. You guys are familiar with cameras here, right? We got these cameras that was on a tripod, and we would just drop them down. It was just a fascinating thing. We had hooks because it's a hook and line fishery with bait on the hooks, and it was just like a lot of fun to watch this. So we'd see the rockfish come up, and then they would come and they would sit there right next to the bait, right? And they would just sit there. I don't know what they were waiting for, but they were doing something there. And then this octopus came in, this giant octopus, and its arms were out like, I'm king of the world. You guys all get out of the way. And all the rockfish took off, and it started to settle in to look at the bait. And then this giant halibut came in, and the octopus turned over, said, I'm just a little coral. I'm going to just move out of the way. So then we pulled the camera up, and the halibut followed the camera all the way up to the surface, whatever it was, 90 feet or something like that. And so it's not surprising that they do this all the time. And so we think of halibut as sitting on the bottom, but they're actually, like many other things. And in fact, I did a lot of work on halibut movement, and halibut will move from Washington, Oregon, up through into central Gulf of Alaska and back annually. So it's kind of like a migration like a salmon would do, only they don't go up in the streams, they're just moving back and forth. And the fidelity is, we'll tag a fish, and then it'll be there like 5 years later in the same spot. So they're going up and they're coming back, but somehow they're returning to the same locations. So the preferred temperatures seem to be 8 to 22 degrees C in the spring, and then some kind of shift, 20 to 25 degrees in the fall, as the plot showed. We were using a random walk with time, and that seemed to do better than year. So the random walk, I was struggling with this. I was calling them random walks, where I was thinking like the information from the past was informing where I was going to go next. But in reading the literature more deeply, what they're calling a random walk is actually more of a smoother that takes into account information in the future as well as the past to determine where it is. They're calling it a random walk. I'm calling it a random walk here, but it's like a generalized additive model, if you will, some kind of smoother operating there. That did better than me having separate parameters for each year. So effectively, it reduced the number of parameters, and in this case, the trends are relatively linear, as you noticed in the time trends that I showed. And so having something that was like a smoother worked better than having individual year effects calculated in there. We noticed, of course, a northward shift in density, which was really important. And the RN is a useful modeling structure, I would argue. I'm going to continue to use it for characterizing the spatial temporal trends. So I could run something like this, and it would take a few minutes, but that would be about it. If I was trying to do an MCMC for just one, it would take about a half hour, 45 minutes for me to do that, right? So imagine me trying to do that. So I'm going to use this and the geostatistics. Geostatistics in the Barents Sea from the Institute of Research. I have 20 years of acoustic data. So here I had the National Marine Fisheries Service statistical areas. There's like 30 of them, all right? So that's 30 points over 20 years, right? With the sea surface temperatures and so on associated with that. There I'll have thousands of acoustic observations over a 20-year period for multiple species, right? So it's taking me a little while to kind of move into that. I'm kind of being a little careful about it as I'm looking through it. But I'm thinking this method, and I know some of you might be interested in this method can be really powerful. The procedures out there are not fully documented yet. It's kind of like 80 Model Builder, the one that's used for population dynamics. For many years, that wasn't very well documented, and then people started asking questions, and then you could get online and figure out how it works. We're kind of 2 years into that now. So a lot of this is sort of figuring it out on your own, but eventually trying to use it. So thanks for listening. This is Furneaux Hall. Alex, you might remember that. I was told back in the day when my boss at the Halibut Commission, Don McCochran, who actually was a Cornell alum also, Don talks about how the snow was up to the top of the door and that they had to walk from the graduate student parking lot across the street where the soccer stadium is now. These days we get maybe 10 inches of snow and that's about it, and then it melts off in a week. So is climate change happening? Yes, I think it is. So anyway, that's my talk. Questions?